Hello everyone, I'm Lana Ahmadi and we are gonna review basics of statistics on chapter 1. So chapter 1 is the statistical background, as you can see here. The course notes are copyrighted material at Professor Alex Penlidis. If you want to share the notes with someone who is not in our class, please contact Professor Penlidis and get permission from him. You can see his information on the first page that I showed you. Okay, so these are major topics. You will see that when we go through the course, I will add more and more. Chapter 1, you can, if you want to read from our book. So this is the design and analysis of experiment. So it's a reference book that we have. It's chapter 2 of this book mainly, but I try to cover everything in this chapter as well. The things that we are going to, subjects that we are going to use in this course, it's written in the chapter. So this is the review, basic statistical concepts. So these are the parts that we are going to cover, like review impact, random variables, experimental error and measurement, mean and variance, random sampling and sample statistics, normal distribution, central limit theorem, confidence intervals, t-distribution, hypothesis testing, variance ratio tests that we have for the chi-square and the FS distribution. So basically the tables that we are going to work with in basic statistics is like Z table, T table, F table, and the chi-square table. And we're going to go through them. It's going to help us to find out the probability without calculating the integral for the probability, because probability is the area under the curve, right? So instead of calculating the area under the curve, what are we going to do? We are going to go to some tables, and based on the information that we have, like, for example, the number of the samples, or what is the confidence interval that we are looking for, like if it's 95% confidence interval, so the alpha is going to be 5%. So these are the things that we learned in the second year stats. Based on those data, we are going to go to the table and find out the probability. So that's the reason that we have all of these basic stats table, and we're going to work with them. So why a statistic? We can think this way, that to answer these questions, what role does a statistic play in, like, scientific endeavor, the historical origin, the measurements, like it's a data analysis, right? So I'm sure that most of us, we heard about this, like in the news, or like the simplest example is the weather forecasting that we have. It's like you gather the data and analyze the data and generate the linear or non-linear model. These are all stats when you hear about them. So statistics deal with the gathering and analysis of data. So while I'm talking on these slides, I will I try to talk about the, like, whatever we have learned already in the second year stat, and I try to refresh our memory on this. So for example, for the analysis of gathering of data, we have 3 different types of gathering data. We would say it's a historical data. We call them retrospective data as well. So we have the observational data gathering. It's like that. You don't do anything. You just go to the plant and record the data. And also we have design of experiments. So or experimental design, which is the main topic that we have here. So the experimental design is like that. You would go to this plant, like let's say distillation column plant, and then you play with some items, like you would change the pressure to see the effect on the product. So that's the design of experimental. So what part you are going to choose to play with, that's how you would design your experiment. So these are 3 different types of the data gathering that you can see here. Here's that what quantities that you deal with have variability associated with them. Like, for example, this is when we are working in statistics, we can answer all of these questions, right? Statistics help us with the decision making in the face of the uncertainty. So it's like that, yeah, especially error, right? During the process of decision making, we are interested in statistical inference. So basically, it's like this: we have a population, let's say in whole Canada, and then we want to make a model for our population. So we are going to get a sample, right? And we try to have an unbiased sample. So when we get the sample, so based on those, we are going to choose one of those three or mix of those three data gathering methods, and we are going to get the data for our sample. Let's say, and then you are going to make your model for your sample. Would anyone buy that model from you? No, because it's just going to work for that sample. So what are we going to do is that we have some statistical inference to connect that sample result to the population outcome, the one that we are looking for the population. So it's like this. Think this way. We have the population. We are going to get that data from the population, but in a smaller scale, like as a sample. And then we want to go back to the population. We are going to make the model for the sample. We want to go back to the population. So we need something in between, right? So we would say a statistical inference here. Here is the process of stating something about the population based on a sample that you have. So the tools that we are used mostly is the confidence interval and the hypothesis testing that we are going to review in this on this chapter as well. Random variable. So the variable that we want to build our model for on that, it should be random variables. So random variable is a chance quantity, like a mathematical variable whose value is determined by chance. When we perform an experiment, there will be some unique value of the random variable, which will correspond to the outcome that we're looking for. Like, for example, in the weather forecasting, so you would say that, so you want to know that, let's say you would like to know the temperature, and so the outcome is temperature, and then your weather, you're going to have some random variable that your temperature depends on those variables. It can be like day of the year, right? Or time of the day. Like time is one of the variables that we consider in the forecasting. Or you can say that the sun, like historical data that we have from the sun radiation. So that's another variable that we consider. So here's that the value of the random variable cannot be predicted with certainty. Yeah, it's like because the outcome of the experiment cannot be predicted with certainty. So it's like that we can't be sure about it's a statistic, right? So everything is prediction. However, we can usually express some knowledge about the possible value of the random variable, and that's the result of our model. Like when we forecast something with our model. A statement of the probability of all possible outcome of a random variable is called the probability distribution or probability density function. We differentiate between the continuous and a discrete random variable. So we had it in the second year stat as well. It's like that when we say continuous random variable is like that. For example, think about the interval of a time. That's continuous that we consider. And then the discrete random variable is like that when you have exact number, like number of people, that's discrete random variable. The reason that we differentiate between these two is that in statistics, when we want to work on the probability distributions, we have different categories. So each of these categories that we are talking about is like that. It's going to be for the, like, for example, continuous, or it's going to be a discrete one. So an example for the discrete distributions that we had so far, is like that. For example, binomial distribution. Like think about the playing basketball. You're playing with the balls. If you are going to shoot the goal or not, that's going to be it's yes or no, right? So that's the outcome is 2, success or failure. or head or tail from the coin. So that's we call it binomial distribution. And then for this binomial distribution, which is the subsection of the discrete random variables, we are going to have hypergeometric, for example, distribution, or we are going to have like negative binomial distribution. We're going to have Poisson distribution. So each of these distributions, we have equation for finding out the mean, variance, and also probability like function. When we are talking about the discrete random variable, we call them mass distribution, probability mass distribution. And when we are talking about the continuous one, so we are going to have different names for them for sure, and different equations. So for example, for the continuous one, we would say gamma distribution. Or like when we will see that in reality, most of the distribution that we use is the continuous, is for the continuous random variables. And we call them probability density distribution or probability density function. So whenever you hear mass distribution, it means that your random variable, it's the discrete random variable. And whenever you hear continuous density distribution, density function, it means that your random variable is the continuous random variable. If you look at the like course notes of the CHE 220 on chapter 4 and 5, chapter 4 is talking about the discrete random variable, and chapter 5 is about the continuous one. So it goes to the details of all of these different distribution that we have. So the next thing is experimental error. When an experiment is carried out under that what are as nearly as possible the same conditions, the observed results are never quite identical. So we have some errors, right? And most of the time there are uncontrollable ones that we are concerned, like experimental error or variation, human error, uncertainty, noise. Sometimes we can control them, but still they're error in the category of error. It's not that we can control them and we can consider them as a variable. I'm going to, in a few slides, I'm going to show you the general model that we have from this. In a statistic, error is a technical, emotionally neutral term. So we can fight with the error. It's always there. I've been working in this field right now for more than 20 years, I can say. And it's like that with the statistics. And I taught this stats course. I'm not sure, it's like that 11 times, 12 times, something like that, here at U Waterloo. It never happened that we developed a model without error. So it's going to be always there. We can't blame it. And the sources can include the measurement, analytical sampling, ambient condition, like human error, all of those ones, age and purity of the regions that we have. And awareness of the potential sources of error is going to help us a lot. And the effects of the experimental error is essential in the design and analysis of experiments. Because it's going to help us. We will see that like from chapter 3 of this book, of this course, we are going to start working on the real experimental designs. We just need to review these things before, and I add whatever we need to use in this course to the review section as well. It's like that. It's 70% review, but it has 30% new things as well that I add to this chapter 1 and 2, just to make it more useful for us while we are working on the design and analysis of experiment. Experimental error is a random variable, but it is a random variable, but it's not that we can consider it in a way that we develop, when we are developing a model, we find a coefficient for it. So for example, we would say, let me give you another example, like electricity load of this room. I would say the electricity load of this room depends on the number of the people that they are in the room, weather outside, because we have like lighting, we have the heating and cooling load, appliances, electricity consumption. So I would say that if I consider all of these as random variables, at the end I would say all of these plus some error. So what we do in a statistic is that we are trying to find out coefficients of these variables. Like, for example, I would say electricity load is equal to, and then I would say, for example, beta null, the first constant that the intercept that I would have, plus beta 1, temperature outside, which is the first random variable, and then plus, like, let's say beta 2, the number of people that I would have in the room, and then plus, like, other variables that we would have. At the end, I would say plus the epsilon or E, which is my random variable for the experimental error. But I can't find the coefficient for this error. It's like that, we will see that in our calculation, we would say this is just an error that we consider. We will add it to our model, linear or nonlinear model. And these models, linear and nonlinear, we call it regression models, by the way. Okay, so experimental data and experimental result, or data in scientific work, is often a numerical measurement which describes the outcome of an experimental run, so trial and treatment. We talk about these things a lot while we are, like, from chapter 3. One very useful way of dealing with the measurements is to hypothesize the following model. So this is the model that I told you, like, in few slides before that I'm going to show you. Look at here, it says that y is our outcome, or it says that it's a random variable representing the experimental data for the ith experiment, the outcome of that experiment that we are talking about. Mu is the true value for that experiment, and then epsilon is going to be a random variable representing the experimental error for that ith experiment. So that's the, so it's always like this. This epsilon, we have a range for it. We would say that, or we would say it's a maximum amount for the error. The error epsilon cannot be predicted exactly, as I said. It's like that we are going to have a range, or we have a maximum for it, but can be dealt with using probability theory. So mean and variance, these are the basic things. There are 3 items that we are interested while we are working in basic statistics: mean, variance, and variance is the same as you get the square root of it. It's going to give you a standard deviation. So it doesn't matter if I say mean, a standard deviation, or mean and variance is the same. Mean, variance, and density function. So it's very important that we can calculate these ones. When you want to find out the density, or density was for the continuous one, right? And when I say density function is the same as the density probability function, right? It's a kind of probability function that we call it. I would say probability function, or the only thing is that when I say density, it means that our variable was continuous. If I say mass, our variable is the discrete ones. So we need to calculate mean and variance, because it's going to help us in calculating the probability function. There are quantities used to summarize information about random variables, like this mean and variance, and their probability distribution. So it's going to help us with the probability distribution, as I said. So the mean, we call it central tendency as well. It's the same, but we would use mu or mean. When it's mu, it shows that it's the mean of the population. If it was mean of the sample, we would call it X bar. So the mean is a measurement of location. As such, it represents the typical value of the long-term average value of a random variable. Mean exactly, in fact, it's exactly the expected value that I have. For example, for my, let's say for when we want to cut this post-it, right? So the expected value that I have from the catalog, I call it mean of the mu. So, and then I would gather, get 100 samples of this one, and then I'm going to measure this to see that if it's going to match the expected value or not. So X bar is the one that we calculate from the sample, which is the mean of the sample. But mean of the population is our expected value. It's what we have, it's what our designs tells us to have it for our product. because of that, we would say that as such, it represents the typical value or the long-term average value. Because in a long term, we are going to design our, like, the product should match the specification based on our design, right? It also refers to the arithmetic mean or expectation. It's our expected value. So look at here, E of x equal to mu, and as I said, you can add it to your note here that the mu is it means that means of the population. And then we would say it's equal to the sigma, because it's discrete, so it's like that we are going to add, like, from the first variable, from the first data point, and then from the second data point, third data point. So it's like that they are discrete. So you would see that we have sigma x of p of x. So whenever we are working with the discrete, for the probability, we call it p of x. And then you can see that in the continuous one, it's very similar. The only thing is that because it's continuous, we don't have like individuals that we can add them, like, let's say 1 marker, 2 markers, that we could add them like that. It's a range of the variables. It's continuous. So what would we need to do is that we need to get the integral. So it's very similar. It's like integral of x, f of x. So when we have the probability density function, we use the f, like a small f of x, right? So that's the probability density function. The next thing is variance. The variance sigma 2, and again, this variance is for the population as well, is a measure of dispersion or a scale, having established a typical value. Let me see if I'm recording. Let me just, yes. So the variance that we have, if you get the square root of the variance, it's going to give you the standard deviation. In fact, it's like deviation from the mean. So look at here, it's like the variance of x, or sigma x, is the expected value of x minus expected value of the x. So in fact, that expected value of x, like the small one inside the parentheses, that one is the same as mu. And look at here, so we have the x, is this one, right? Mu, or this one, it doesn't matter. It's like that. If we have the discrete, we are going to go with this. If we have continuous, we are going to go with this. But it's like the x minus expected value of the x, like x minus mu. So think about it. I have some data points, and then I'm looking for the deviation from the mean. So if I square them and add them together, so in that case, it's going to give me the variance.